Okay, so I start with a solution here. As I see, many of you try to do inequalities with this independence number together with the degree. But here, actually, the argument is much simpler than that. You just have to look at what will happen if you color a graph using a maximum chromatic number as your R. So if the chromatic number is, say, R, that means there is some coloring of this graph using R colors, okay? But R colors means when you use those colors, say if you use the black ones, and then you use the red ones and the green ones, you cannot have edges between same color ones, right? So these are the... So that means in your graph, the green ones they don't have edge between them. So some of the edges could be like this. Could be having a graph like this, but you cannot have edge between the same color ones, okay? So the rule about coloring was that the vertices which have an edge between them cannot get the same color. They have to be colored in different color. So if you if you say the red ones are, say, S1, the green ones are S2, in this case, actually, I should probably make those numbers different so that these numbers are different. That gets the eye color. So you can actually see that all vertex set is just the disjoint union of these different sets which gets certain colors. So this is union of green ones, black ones, and red ones. Okay? So a vertex set is naturally decomposes to these green ones, red ones, and black ones. So that means you can say n, the number of vertices, is actually sum of these number of things inside them. So here you have 3, 3, 4, totally n equals 10 vertices. So here you're summing 3 plus 3 plus 4 to get 10. But what is the thing about these things? Like what you can see about the green ones, they cannot have edge between them, right? So if you just focus on the green set, that should be an independent set. If you focus on the red ones, they should be an independent set. So each of these actually is an independent set. That means the independence number of the graph should be bigger than all of these. Your independence number, in this case, for example, it is 4. It's bigger than all the number of green ones, number of red ones, number of any of these same colored ones. But if you are summing things over a set and each of them then their maximum, say m, this maximum will be bigger than all of these, right? So it's the same as summing the maximums, which means you're actually maximum times number of things you're summing. But what's the number of things you're summing? How many sets we're talking about we have here? You have R sets because this is number of chromatic number. Okay. So you actually see that the maximum times R is bigger than n. And we just saw m is less than that, so I can change it with the independence number. So this is the inequality I get, that independence is bigger than n divided by r. So that's the proof. This is one of the harder ones, maybe. Let's solve some other ones, and then you can see not every question requires a lot of thinking. I have some quizzes that are being graded, which you can pick at the end of the lecture if you want. But except the last one, it's all the quizzes that's being given, is being graded. Okay, let's start with one question. How many people solved 4? So that we don't solve the ones that you solved. Anybody solved 4? Except Julia. Again, Julia was the only one who came to the office hour yesterday and asked me all the questions that she didn't solve. And anybody who solved 4? Okay, let's start with 4. Or let's start with something relatively easy, and then we move on to 4. Okay, this is from the sample. I will solve a question which I think it's much easier than any of the other questions. And then I'll solve a little bit harder ones, and so on. So if G is a connected graph with 17 edges, and if degrees is bigger or equal to 3 for all V, what is the maximum value for V? So how many vertices I can have on a graph where degree is bigger than 3? You should see that if you have more vertices with the number of edges constant, your degree will go down, right? So because degree is already told you is given as bigger than 3, there must be an upper bound for V. So we are asking, what's that upper bound? Do we know anything that relates number of edges to number of to degrees of vertices? Anything? Huh? There was something, right? So, huh? Huh. So if you sum over the vertices the degrees, degree means the edges attached to a vertex, right? So here degree is 3, for example. And here degree is 5. So degree is the number of edges here. This is the number of edges here. So degree means, this is I, this is J. Degree J is 5. So degree means number of edges attached to a vertex. Now if you sum all the degrees, then you're summing these edges between two vertices twice. One as part of this, and then twice as part of this. Because of that, this sum will give you exactly 2 times the number of edges. Right? That's that. Now, if you know that each of these is bigger or equal to 3, from this you can conclude that this is going to be equal to, from this you get that 2e will be bigger or equal to sum of all these 3's, because 3 is bigger than 3, which means 3 times the number of vertices. We are given that E is 17, so V should be less than equal to 2 times 17 divided by 3. So how big that number is? 34 over 3, it's 11 point something. So what's the maximum value we can take? 11. Because it has to be integer, it has to be smaller than this. So maximum is 11. This is all you do. You just remember this formula and use it efficiently, and then you have a solution. Now something a little bit harder. Prove that for each n positive integer, there is a loop-free connected undirected graph G where prove that for each n there exists a loop-free connected undirected. Now, this is an important remark I should say. This undirected and loop-free is often stated in problems from Grimaldi, but in problems that we did in the class, we do not actually emphasize that something is loop-free and undirected, because when we say graph, we already mean that it's loop-free undirected. So in the exam, if you see only graph, you can assume that it's loop-free and undirected, okay? So this undirected and loop-free, it's usually put there in the book Grimaldi, but in our lectures from the beginning, we said the graph means loop-free and undirected. So like in this question, when I say graph, we don't think that it's directed, we don't think that there's loops. So you should always assume that it's loop-free, undirected. Loop-free means you don't have things like this. And you can see that we never drew them, right? So we can safely assume that your graphs don't have them. So in the exam, I usually won't give those, okay? Just assume them all the time. But connectedness is important. Sometimes graph may be not connected, so it has to be given to you that if you want to say it's connected. Okay, so how can you make a graph who has exactly 2 of each degree that's available between 1 and n? The hint is you should actually, anytime this is 2n, you should think it as like you have 2 sets of vertices, and you should somehow use the fact that it's twice of some number. For example, for n equals 4, can you draw a graph which has 2 vertices with degree 1, 2 vertices with degree 2, 2 vertices with degree 3, and 2 vertices with degree 4? Say we want to get a degree 4 vertex, you go like this. This is now degree 4. We want to get a degree 3 vertex, you go like this. When you get a degree 2 vertex, you do like this. Degree 1 vertex, like this. And then, voila, this degree is 1, degree is 2, degree is 3, degree is 4. So you got 2 vertices with degree 4, 2 vertices degree 3, 2 vertices degree 2, 2 vertices degree 1. So you just have to set your graph, this generalizing this to n. Basically, you need to, from 1 to go everywhere, from 2 go everywhere 2 and bigger, from 3 go 3 and bigger. So for I, you need to go to the I prime and bigger. That will give you a graph where you have exact even number of everything. That's the answer. Okay. Let's do one more question. Maybe we can stop earlier today. Already 14. So one more question, then we'll stop. If you draw graphs, you notice that after a while, there's always 2 vertices which have the same degree. You can try to draw any graph. Degrees are, so there are 2 vertices with same degree. So if you try to increase the degree, now you have 2 vertices same degree. If you try to put them more together, you see that now there's 2 of them. And then there is this 2. Whatever you do, you cannot avoid having 2 vertices with the same degree. And the question is, this is always true, and show why. Any ideas on how you can show this? And you can try to make it more tense, but you always have like 4 and 4. Make this 5, then this 4 is same as this 4. This is 2, 3, 2. You cannot make a graph with all the degrees are different. You can even try to disconnect the two graphs, like it still doesn't work. So there's 3. There's 3 here and 3 here. Any ideas how this can be solved? This is a question that's solved by using pigeonhole principle, the principle that we learned at the beginning of the we learned after first midterm. Anybody remembers pigeonhole principle? There's this pigeonhole principle. If n pigeons are distributed to m pigeonholes, and if n is bigger than m, then there exist two pigeonholes more than 2 pigeons. So at least one of the pigeonholes gets more than one pigeonhole. More than one pigeon, or equal or bigger than 2 pigeons. So the idea is, in the pigeonhole principle, in all the questions we had pigeons and pigeonholes. So in the solution of this, you should also have pigeons and pigeonholes. So to make it simple, assume G is connected first. Set up pigeons and pigeonholes. So that if one of them, more pigeons than pigeonholes, will tell you that you have at least 2 pigeons going to the same pigeonhole, but that conclusion should give you that 2 of the vertices have the same degree. So what should the pigeons be? Should be vertices, right? So pigeons are vertices. So as I said, these are your vertices. And there are, say, n of them. N vertices. So what are the pigeonholes? These are the integers that we will assign the degrees.